Hello, today we are going to identify unknown elements, but in more complex nuclear processes, which you can see in this case on the screen. Not always reactions are nuclear simple, they can be accompanied by the interaction of alpha particles, beta particles, and gamma particles. In this case, protons, positrons, and neutrons can also participate. And that's how to solve such tasks. Let's learn today. The following nuclear reaction is proposed, in which there is an element unknown to us yet, which turned out in this case. So, the element samarium is taken, 96 number 242 of its mass, and it is subjected to the action of an alpha particle. The alpha particle, recall, is the nuclei of the helium atom, 2 and 4. It has passed by this process into the element californium, 98 245, and in doing so, some other particle is formed, which has an unknown number, and consequently its mass. So how do we determine what chemical element it is? We will work by means of the Sodifayans rule, or this is a manifestation of the law of conservation of mass and energy. We work as follows. Let us first determine what is the mass of this unknown element. To do this, we work like this. We have 242 on top. The alpha particle is 4, and on the right-hand side we have californium 245. Well, it's not hard to do the math. We've got a mass on the left side of 246, and since that leaves us with 245, then for an unknown particle this A is equal to 1. Now we need to determine which element this is in terms of its unknown charge. So let's see how things work out here. So we've got 96, we've got 2 here. And californium has 98. Well, let's see. On the left-hand side, we have a sum of just 98, just like the right-hand side. And therefore, our unknown element will have Z in this case equal to 0. Then what do we get? The fact is that the particle that has a charge of 0 and a mass of 1 is the neutron. It's this particle that will have this data. So this element, well, in this case, this particle will be the neutron particle. So it's the neutron particle that's missing in this reaction. So, well, now let's look at this process. And here we have the unknown particle on the left side. So we need to determine what element we're going to have. And here we found Z, so we're going to start with our mass. So we have an unknown mass, and then we have an alpha particle which equals 4. And on the right-hand side we have 243. And from the neutron we have 1. Then it turns out that on the left side we have a yet unknown 4, and on the right side we have 244. From these 244 we will subtract 4, and then we still have that A will be equal. It turns out to be 240. Next we need to determine what Z is here. Now in this case Z is not yet known. Z plus 2 is on the left-hand side. And on the right side is 96 plus 0. Then it's clear that we have 96 on the right side, but the left side must also add up to 96. And so Z in this case will be 94. Well, it's the order or atomic number that plays a major role in the first place. The 94th element is plutonium. It's 94, and one of its isotopes is 240. So the unknown element that we have here is the element that's going to be plutonium. So the next example, we have the element California, which is treated with the unknown element and goes to Laurentius and gives 4 neutrons. We work in exactly the same way. First, we need to establish that here we will have A. To do that, 250 plus the unknown mass A equals 257. And the fact that we have 4 neutrons here means that we multiply 4 by 1. Then we can calculate that on the right side this will be 261, and then we have on the left side A turns out to be equal to, if we do the math, will be equal to 11. Now we need to establish its atomic number. So this element has 98 plus a number we don't know yet. And on the right hand side we have 103. And since neutrons, even though there are 4 of them, but the charge of the neutron is 0, it still turns out to be 0. Then on the right side we have 103. And since on the left side we have 98, Z will obviously in this case equal 5. Let us then ascertain which element we have had taken. Since the principal is its number 5, the 5th number has boron, it's number 5. And its isotope is equal, in this case with a mass of 11. So, the unknown element that has been encrypted here is boron with mass 11 and number 5. So on the left side, we also have an unknown element in the last example. And we have to find out what this element is if it interacts with carbon. It turns into the element nobelium and splits neutrons as well. So we don't know what the mass would be for this element. A plus 12. And on the right side is 254. And since we have 4 neutrons plus 4, then we have 258 on the right side. But since we must also have 258 on the left side, we conclude from this that A in this case we will have equal from 258. We subtract 12 and we have 246. It remains to establish what Z will be in our case. So Z plus 6, that's from carbon, equals 102. That's nobelium number, and since we have 4 neutrons, but neutrons have a charge of 0, we get 0 in this case. Then we have 102 on the right side, but we have 102 on the left side. And in this case, for this unknown element, we have Z equal to 96. But since in this case Z is the main value for identification, we will conclude that in this case the cipher was samarium 96 and its mass 246. That's what was cipher. So in this case the unknown element was the element samarium. I hope from the examples we have made it is clear how they work. These calculations are not very difficult, and these reaction equations themselves are quite simple, and I hope you understand how to work with them. Of course, when such processes are carried out in practice, it all looks more complicated, and these nuclear reactions are accompanied not by one specific nuclear reaction, but by many such interactions, which can go from decays to captures and so on. There are notions of nuclear chain reactions, which also take place for nuclear, chemical, and physical processes. How to work with such equations, I hope, has become clear. Well, that's all for today. Goodbye.